so hard. I mean, honestly, look at this. Intermolecular forces, VSEPR models. I mean, I guess I understand that intermolecular forces are what hold molecules together, and that VSEPR models show how atoms in a molecule are arranged. But what the heck is a dipole moment?
Did somebody say dipole?
Who are you?
Well, I am the chemistry genie, of course, queen of the dipole.
Really? Can you help me with this impossible poggle?
Yes, of course, that's why I'm here. Your moment has come, young pupil. The dipole moment, that is. Grab my hand.
Wait, dipole moment?
To the lab.
Whoa, what is this place? Who are you?
I'm the chem whiz and this is a teaching lab. So you say you need help with dipoles?
Yes please.
Well, Jeannie, what exactly is a dipole moment?
That's a good question.
But first, let's start with a brief review of electronegativity. This periodic table shows the electronegativity trend. Electronegativity is the tendency of an element to pull on its electron.
So we know that fluorine is the most electronegative.
Right, and this is important because...
This is important because between a bond, electronegativity determines the dipole moment.
Wait, why?
Well, let's take a look at this model.
The more electronegative an atom is, the more negative, the more pull it has on its electrons. Let's look at a molecule of water. We know that one molecule of water has 2 hydrogen atoms, 1 oxygen atom, and a total of 8 valence electrons.
These electrons account for the bonds and charges of the molecule. But first, let's look at how the atoms are arranged. From the Lewis structures, we know that the most electronegative, in this case oxygen, is in the middle. Then, the hydrogen atoms are distributed around it.
Then what do we do with all these electrons?
Well, first, we use 2 electrons for each bond between the hydrogen and oxygen atoms.
Then, we distribute the rest of the electrons, starting with the outer atoms. Because hydrogen's outermost shell is filled with only 2 electrons, their shells are already filled. So, we put the rest of the electrons around the oxygen atom, making sure that it has at least 8 electrons.
Looks good. Now what?
Well, do you see these lone pairs of electrons around the oxygen? They repel the hydrogen atoms some, so they are arranged like this.
Then, because oxygen is so electronegative, the electrons from the hydrogen-oxygen bonds are drawn closer to the oxygen atom, making a polar bond.
Wow, look at all those electrons around the oxygen atom.
I know, right? Well, electrons have a negative charge, so the negative charge is concentrated around the oxygen atom.
And because the molecule isn't symmetrical, the polarity doesn't cancel out, so the negative charge of the whole molecule is concentrated around the oxygen.
We denote these concentration of charges with this funky arrow we call a dipole moment.
So then, is the head of the arrow always pointing to the negative side?
Yep, then we cross the other end.
Like a plus for the positive side.
Cool, but can something like CH4 have a dipole moment?
Well, let's look at its structure. As you can see here, this molecule is symmetrical. All the atoms surrounding the carbon are hydrogen, so they all have the same electronegativity, or equal pull on the electrons. This means that the polarity of each bond is the same. So because it is symmetrical, the polarity of each bond cancels out. So we can say that CH4 does not have a dipole.
Okay, so I'm guessing that a temporary dipole means that the dipole isn't always there, but then what makes it relevant?
That's a great question. Well, you know, molecules aren't just floating around, otherwise nothing would be solid or liquid. Things called intermolecular forces, or IMFs, hold things together. Temporary dipoles are important because they interact with something called London dispersion forces, one of the IMFs. But that's another story. One of the stronger IMFs is a dipole-dipole force. An example of this is water.
Whoa, what are we doing here? What is this place?
This is what we call the Mason of potassium oxide.
So basically we're at a lake, right?
Precisely. Now let's look at the water. This lake is full of water molecules like the one that we made earlier. Remember, this molecule has a dipole moment with the negative part pointing to the electronegative oxygen atom.
When more than one water molecule comes close enough together, the positive side would be attracted to the negative side. See, that's what's happening in this lake. Positive and negative, then water.
Cool, so molecules that have different electronegativities have dipole moments, right?
Exactly. And then the ends with opposite charges would attract, forming dipole-dipole bonds.
But wait, there's more. It just so
what exactly is hydrogen bonding?
Well, let's take a closer look.
Let's take a look at the magic of biochemistry.
First off, we know that the attraction that occurs in hydrogen bonding is stronger than anything we've seen in this video.
Hydrogen bonding is when the element hydrogen bonds with any of these three elements, nitrogen, oxygen, or fluorine.
Just think NF.
Do you mean NOF?
Same thing. But not just any molecule with nitrogen, oxygen, or fluorine can hydrogen bond. They have to be part of a polar molecule and have an unshared pair of electrons around either the nitrogen, oxygen, or fluorine atoms. Do you remember when we were at the lake? We were surrounded by water molecules, just like this one here.
And don't forget that because oxygen is the most electronegative atom in a water molecule, the electrons are drawn towards it, creating this dipole moment.
Yup, then the hydrogen of one water molecule can form a hydrogen bond with an oxygen of another water molecule. Because oxygen is so electronegative, the hydrogen electron is practically taken off, leaving the hydrogen atom to act as a proton. This means it can temporarily bond with the negatively charged oxygen of both molecules.
That's right, and remember both molecules don't have to have a hydrogen atom in order to hydrogen bond. Only one needs a hydrogen and the other needs one of the NOF elements with a lone pair of electrons. Here are some examples.
I think I get it now.